So last time we had the first example, if you remember, it was this turned out to be a hyperbolic function. It was, if you remember, e to the x and then plus e to the negative x and so on. Today's example, and this will be example 2 in this topic, we want to find the arc length of the parabola and the parabola is y squared or x equals y squared. Okay, and again we want to go from a certain value to another value, so we go from 0, 0 to 1, 1, like so. So how we go about solving it, let's just visualize the problem first. The parabola y equals x squared is a vertical parabola. The parabola x equals y squared is a horizontal parabola, if you remember from pre-calculus. The vertex of the parabola will be at the origin. And you can tell that this is not, y is not a function of x, as we failed the vertical line test, but in this case x is a function of y. In any event, it won't be a one-to-one function, and we go from 0 to 1, like so. So we have 0, 0 as the starting point, 1, 1 is the end point, and this is r, the length of the arc is this piece right there. So L is the length of this piece. All right, so we'll go with the definition, and here we have x is g of y, so we're going to use the second definition, or the second representation of the arc length theorem. So we go, in this case, we go on the boundaries on y. Y goes from 0 to y equals 1. In this case, it doesn't matter because 0, 0, 1, 1. But for instance, if we went from 0, 0 to 2, 4, right, then the boundaries will be 0 to 4. The boundaries on y, the boundaries on x would be 0 to 2, the other way around. The boundaries of x will be 0 to 4, the boundaries on y will be 0 to 2, because this point will be x equals 4, y equals 2. But we went 1 to 1. But I wrote the boundaries like to install this idea in your mind that you need to verify that you're putting on the boundaries the y value rather than the x value, as dy or y is the variable of integration. So what we have here is 1 plus dx dy squared dy, or I'll write it as the integral from 0 to 1 of 1 plus g prime of y, like so. So far what I did is I rewrote the theorem, and now let's find out what is dy, what is g prime of y, okay? Squared, yes. It says squared here. You just don't see too well. Okay, so g of y equals y squared, and therefore g prime of y equals 2y, and therefore 1 plus g prime of y squared is equals to 1 plus 4y squared, right? So what is the integral? The integral L is now, looks like this. The integral from 0 to 1 of the square root of 1 plus 4y squared dy. So what do we do at this point? Integrate how? What technique should I use here? And I don't want you to look at the table. Let's say this is test situation. Table is not available to you. What is available to you is your brain. No. No, not a sine. Tangent. Tangent. We're going to say that tangent theta will be 2y. Okay? Therefore, secant squared theta d theta will be 2 dy, or dy equals 1/2 secant squared of theta d theta. So, what happened now is L well, we are not out of the woods yet. I need to replace the boundaries, okay? So let's write it when y equals 0, right? Then, because y equals 0, then tangent theta equals 0, and therefore theta itself equals the inverse tangent of 0, which is 0. Because again, the tangent defined here from negative pi over 2 to pi over 2, and that's in order to be a one-to-one function or invertible function. So the only value of theta that makes tangent theta equal 0 is 0. So that's not an issue. A bigger issue is what happened when y equals 1. Okay? The tangent theta equals 2y, so it would be 2 times 1, right? So theta, in this case, and just that would be the upper bound, it will be the inverse tangent of 2. And I'll leave it at that. Now, this is not a special angle, so we cannot come up with a nice expression. It's just a number here, and I'll leave it at that. And now I can write the following. L, in the new dress, after all this substitution, will be the integral from, instead of 0 on y, it will be 0 on theta. So I write theta equals 0 here. The upper boundary, theta, will be the inverse tangent of 2. Okay? So you can write theta 1 and theta 2, and keep in mind that theta 1 is 0, theta 2 is the inverse tangent. Okay? And now we're going to plug in. So, the square root of 1 minus 4y squared is 1 plus tangent squared, right? And 1 plus tangent squared is a secant squared, so we have the secant. The square root of the secant squared is the secant. Times dy will be 1/2 of the secant squared d theta. So we are looking at 1/2 the integral from 0 to the inverse tangent of 2 of secant cube d theta. Again, if you're allowed to use table, then you can look it up, but since you are not, then you need to solve the damn thing. So what do we do here? Any idea how to solve that? Separate or... You are dancing about the right idea. First of all, to simplify, let's leave the boundaries alone, let's leave the 1/2 alone, and let's say I integral, and then you need to remember to multiply at the end by half and add the boundaries, okay? So I will be defined as the indefinite integral secant cube. But instead of secant cube, I'm going to break it down to the secant times the secant squared. Now, why did I do something like that? Because this part is the derivative of the tangent. So this is very good to be dv. And this part will be u. So I'll continue with integration by part. Okay? So integration by part, this is a good preparation for the test. So u equals secant theta, and therefore du will be secant theta tangent theta d theta. Okay? dv will be secant squared of theta d theta, and therefore v is simply tangent theta. Now I have the components, and I'm going to say that I, or the integral, I'm interested to keep that secant cube for a reason that will be clear later on. Okay? I, which is the integral of the secant cube d theta, equals u times v. So we look at secant tangent minus the integral of v du, where v is tangent theta and du is secant tangent. Okay? So now I'm looking at the tangent squared, so I'll continue. Nothing to do with the secant tangent, that's already complete answer. So I need to work on the integral here. The integral here will be, I'll write it as, the way I'm going to write it, I have tangent squared, right? But the tangent is the secant squared minus 1. You already suggested similar idea at the beginning, but you wanted to substitute the secant squared with 1 plus tangent, okay? Which may actually come on second thought, may have, no, on second thought, would get it, wouldn't help us. So the tangent squared will be secant squared minus 1. And here I have the tangent. Here I have the secant. So continue to work here. Again, secant tangent. Now watch closely. We have clear the parentheses and we have minus secant cube of theta d theta. And then you have plus the integral of the secant of theta d theta. Now look at this. We have here and we have here. So we have the integral of the secant cube equals something minus the integral of the secant cube. So what it tells you that we can, I don't want to change pages, I'm going to say that 2 integral of the secant cube d theta. And this is something we've done before, equals secant theta tangent theta plus the integral of the secant. Do you remember the integral of the secant? Natural log of secant plus tangent. So this integral will be 1/2 of what we have here. And we are almost home with that. Remember, I is the secant cube, okay, is 1/2 of this thing. It will be 1/2 of, and what we have here is secant tangent plus the natural log of the absolute value of secant plus the tangent. Like so. Okay? Are we good with page 2? Can I take it off the camera? Go ahead, Greg. Right. No, we are back to I because we divided. This is 2I, but this is I because we divided by 2. Now we're going to go back. We have 1/2. We still have this 1/2 and the boundaries. Remember, all I did, I worked on the indefinite integral. And I omitted the C because I knew that I'm going to go back and have a definite integral. And that's what comes now. So you are just half a step ahead of me here. Okay? And this would be what we're going to do now. Remember, we really, L is 1/2 the integral from 0 to the inverse tangent of 2 of the secant cube of theta d theta. So it will be 1/2 of this one. So it will be equals to 1/4 if you divide everything by 1/2 by 2 of the secant times the tangent plus the natural log of the absolute value of the secant plus the tangent. And this will be evaluated from 0 to the inverse tangent of 2, which is a number. So at this point, I'm going to just calculate the value. And if, let's say that this the requirement is to go all the way to the 6th decimal place, so this ends up being 1.478943. And of course, even though it's a 6th decimal digit, it's still an approximation.